section 6.3 is a continuation of the ideas that we covered in 6.1 and 6.2. Now, in this section, guys, I want you to focus. Look up. Thank you. In this section, what we're going to do is we're going to analyze scenarios that we've looked at already, but then consider energy in addition to momentum. So think about the scenarios we've looked at so far. We've looked at scenarios where two objects collide and they bounce off each other. We've looked at scenarios where two objects kind of hit together and they stick together. The example where I jumped onto the chair and then it was one object moving. Or two objects starting off together and pushing apart and separating. So we're going to classify these collisions in a moment, giving certain terminology. Now, the one thing we want to consider is this. When two objects collide, sometimes the objects themselves can deform. What do I mean by deform?
Oh, like they can bend.
Yeah, they can bend. So if you've ever seen a car accident on the side of the road, is there usually no damage done? What do you usually see? What are some things you see in a car accident?
Usually the hood is lifted.
Sure, the hood is lifted up, it's popped up. Okay, what else?
And like broken parts of the bumper.
Broken parts of the bumper. It kind of pushes in like an accordion, right? Like it kind of compresses the front end of the car. So that deformation does not occur without some sort of energy that's needed. So what happens is, if we look at these scenarios, we're going to see that when things deform, energy is needed for that to occur. Or energy is expended in that deformation. Which explains why, if you think about, if you've ever bounced like a bouncy ball or a tennis ball up and down, it doesn't come back to where you started. Right? If you drop it and it starts to come back up, it's not going to make it there. What's happening when the tennis ball hits the ground?
It flattens out and then comes back up.
Yeah, it flattens out. I mean, not all the way, but it flattens or deforms in some sense. It bends, it fluctuates. Ed, Jake, you got to focus. Come on. There's nothing you could be writing down right now. I mean, maybe you're taking notes, but it doesn't look like you're writing. So look up at me at least, or write something. So you drop the tennis ball, it hits the ground. Yeah, in super slow-mo cams, you'll see basketballs and tennis balls. They kind of deform when they hit the ground. Same thing with a baseball, actually. When you hit a baseball off the bat, the ball actually deforms a little bit. It bends a little bit. It becomes what's called an oblate spheroid. A sphere, right? We know what a sphere is. Imagine a sphere that's been kind of compressed a little bit. Another word is an ellipsoid, but an oblate spheroid, the Earth is an oblate spheroid. It has a small bend to it. It's not perfectly round everywhere. One diameter is bigger than the other. So what we're going to see is that when an object also bends and then expands afterward, energy is used up in that bending and expansion. Another possibility is when two objects collide and fuse together. And a good example is when, and this actually does happen more often than you think, if there's a small fender bender, not like a major accident, sometimes the bumpers will actually melt together in the collision. So a car is like maybe sitting still and the other car hits it at a certain velocity. The actual, the shearing of those two, the rubbing of them against each other, like so here's the bumper in the back one, it hits the rear one and it might slide a little bit, heat can be produced. And those two bumpers might meld together. Like, have you ever seen someone do like spot welding? Or where they weld two pieces of metal together by putting heat on it. They put heat on both surfaces and it causes the two pieces to join at one location. That's the fusion of two different surfaces. When that happens, when two things stick together and then they move as one afterward, that's another reason that energy is lost. So we're going to identify in this section when energy isn't lost and when it is lost. Okay, we're going to classify them as two different types of collisions. The examples, or the definitions and the descriptions. So the first type of a collision we're going to call an elastic collision. And an elastic collision, a good example of this is if you were to play billiards or pool, and you hit the cue ball into another ball, it hits the ball, they separate afterward, they don't really deform, they're solids, they're not going to deform like a tennis ball would. Okay, they separate afterward and they move independently. That's the first example of elastic collisions. And in the elastic collisions, not inelastic, but in the elastic collisions, the two objects have a certain amount of energy before they collide, and then afterward, they have a certain amount of energy, and those energies, the sums of those energies before and after, are equal to each other. So we say that kinetic energy of the system is conserved. That's that word, conserved there. And then for inelastic collisions, this is the one where energy is used up. So imagine an object collides and it deforms its shape. Or if it collides and the objects stick together. Okay, they move together as one object afterward. In this case, kinetic energy of the system decreases. And we'll talk about how that works because energy is needed to cause this fusion. So let's write in some equations here. I'm going to write in those spots. So when two objects collide and they're both moving, and then they separate out afterward and they're both moving. Think about your quiz that you had with the baseball and the baseball bat. Now granted, the baseball wasn't moving initially, but hypothetically if it were. If two objects are moving, they collide, and then they're moving afterward after the collision. What can I write as far as an equation for conservation of momentum? What was the equation? And look at your quiz if you need help. It should be your equation from example 2, really, that you were looking at, but obviously imagine that the ball is moving. Ed, what would the equation become for this? Good. And then?
And then you would do the two objects initials, so it would be the M and the V for one I.
Okay.
The M and the V I for the second object. Added.
Good.
M I F is equal to, or M I F V 1F is equal to, or plus V2F and M2F.
Good. Now you don't need the F because the mass isn't changing for the math, but I get what you're saying. Okay. Again, this is the same equation that we already saw. It's not different at all. That's what I'm trying to get at here. You saw this in section 6.2. This was the same equation you should have used in your quiz, except in your quiz, the mass of the base or the velocity of the baseball was 0. So this part dropped off on the quiz. But it's identical. So I keep saying in, as in the elastic, but for these situations with elastic collisions, okay, with elastic collisions, we're going to see that they're separate before the collision and they're separate after the collision. All right, they're separate before and they're separate after. And we also know that kinetic energy is conserved. So we can write this statement down as well. We could say that KE initial equals KE final. KE initial is equal to KE final. So although they have different energies independently, the sum of the energies before equals the sum of the energies afterward. This is not relating potential energy. This is not using springs. All right? Now, if you go on to take AP Physics or study a little bit of physics in college, you'll see examples where, yeah, it's shot from a spring, it then collides, it's in the air, so you've got a lot more going on. This is just simply put, the kinetic energies are the same. The energy in the system is conserved. Is this really ever going to happen in real life? It would only happen where? In a frictionless environment, yeah. Somehow in a frictionless environment. So maybe in outer space. Okay, in outer space, yeah, this definitely happens. Now, this happens, and this is only true if the objects are solid. They're not going to deform at all. Okay, but realistically, in real life, there's always some deformation when two things collide, whether it's minuscule or not. Even if it's like, imagine two cars, just little, like you ever hear of a love tap? Have you heard that term before, love tap? When you like bump the person in front of you lightly with your car. If somebody like just lightly bumped the rear end or the back of your bumper's going to fluctuate, right? It's going to bend. That's why it's called a bumper. It's meant to protect, which by the way, I find it hysterical that you see the bumper covers now in the city. Yeah. A bumper is meant to absorb the shock and to be all like dinked up and stuff, to be like, you know, the part of the car that can be all like rusted, or not rusted, but like deformed. And people put bumper covers now on their bumper, which is kind of like you're a cover for the cover kind of thing. It doesn't make much sense, kind of, right? I don't know. I guess people just want to maintain their bumper. But anyway, the bumper is meant to absorb the shock. So if you give a person a love tap, their bumper, it might fluctuate. It might bend a little bit, but it'll come back out. But there's some deformation there. Or maybe it'll bend and it'll stay with a little bump in there. Or a little, a little bit of a nick in there. So realistically, this first part, elastic, it's not really realistic. Okay, there's usually going to be some sort of energy loss. Okay, we're going to assume that there's no friction sometimes and go through those examples, but it's not really a realistic scenario. Now, the second part is also not always a realistic scenario. And I'm going to explain where the realistic scenario comes into play. But the second part is when two objects hit and fuse together and possibly deform. Okay? And they move together afterward as one mass. So, what would my equation look like for the second part? How would it differ?
M1 V1 plus M2 V2 equals parentheses M1 plus M2 and close parentheses VF.
Yeah, because these masses now, after they collide, they act as one mass. Okay, so imagine the example where a person jumps onto a boat that's in the water. You jump on the boat, it's going to cause the boat to start to slide a little bit out toward the water. Maybe it's harnessed in or it's docked, so it's not going to move, obviously. But it's going to move slightly because now you and the boat act as one mass afterward. And you move together. So there's only like one velocity afterward. Alright, so this is the example for inelastic. Okay, inelastic collisions, where they stick together afterward. They fuse together. And we know here that the kinetic energy decreases because there needs to be energy involved in some sort of fusion of those two objects or deformation of those two objects. So in reality, what we have here is this. The energy before is equal to the energy after, but with some sort of additional energy loss. Similar to MEI equals MEF, where you tack on Q loss, this represents the energy loss. And think about it for a second. If the energy of the system beforehand is like, say, 20 joules, but the energy after the collision is only 15 joules, how much energy went into the fusion? 5 joules. Again, 20, 15, this has got to be 5 over here on the right side, Q loss. So the idea behind this is to determine the energy that is necessary to fuse those objects together or to deform those objects. Now, if an object collides, then separates, but there is deformation, that's the more realistic scenario, and that's between these two actually. So you have one end of the spectrum. Ready? They collide. This is elastic, I'm describing the top. They collide, they separate, and there's no deformation. Second scenario, perfectly inelastic. They collide, they deform, and they move together. But what if they collided, slightly deformed, right? What if part of it slightly deformed, but they didn't stick together? That would be somewhere in between these scenarios. Mathematically, it's much more difficult to do that. So we're going to look at the two ends of the spectrum and go with either they separate afterward or they stick together afterward. One or the other. Okay, but in real life, a lot of objects collide, separate, and there's some deformation. That's not perfectly elastic. It's not perfectly inelastic. It's in between those two somewhere. Okay, it's really in between them. Victoria, you had a question before. You sure? Any questions about the differences here? I'm going to do an example and you'll see both of them. We'll do 2 examples today. You'll see one of each so you have an idea what this is going to look like. Okay, but the idea in this section is that our goal is to not only determine like a final velocity or an initial velocity, but to also determine, was there an energy change? If there was no energy change, if there's an energy balance before and after the collision, it's got to be elastic. If there was some energy change, then it's going to be inelastic. Okay, and the energy change that you're going to seek is this Q loss value. The amount of energy that is needed to fuse or deform those objects. Okay? So let's... Can you read it nice and loud for us? Who wants to read? Hey, Jake. Thanks.
An empty train car, mass of 1,500 kilograms, moving east with a velocity of 25.
Now, so the car is empty and it's moving. And it's got little mass. And it hits this other car that has, or this train car that has a lot of mass, but it's stationary. Now, we want to figure out if the 2 cars stick together, find the velocity of them after the collision. So what kind of a collision is this? How would you classify this based on the... Could be? Inelastic. Okay, again, the 2 objects are colliding and sticking together, so there's got to be some energy loss to fusion. And we're going to see what that energy loss to fusion and deformation is of the train cars. Now, in the last class, somebody posed the question, well, isn't this a really fast train moving? I said, yeah, it is. And in this situation, and the train car is moving like 60 miles an hour, that's what that is, approximately. If that train car is moving and hits the other, what's it going to do? It's going to still move, yeah. It's going to continue to push them both together. What's going to happen to the train car that was sitting still? What's going to happen to the body of it?
It's going to get more deformed.
Yeah, it's going to deform. It's going to kind of crumple, right? So we're going to see here that we're going to look in part B for some energy loss. That energy loss has to do with the crumpling of the train and the fact that they stuck together afterward. Maybe the first train car hit it so fast that it kind of wrapped around it and they stuck together as one entity. Okay, so that's what we're trying to figure out in part B. Let's take a look at part A first. For part A, what equation am I going to use? What's the equation for part A? And look at your last slide if you're confused on this. Victoria, again.
M1 VI initial.
M1.
Oh yeah, sorry. M1 V1 initial.
Good.
Plus M2 V2 initial equals parentheses M1 plus M2 plus parentheses VF.
Good. And if you want to say the quantity of, right? The quantity of M1 plus M2 times Vf. So, if I look at this problem, what's not moving? What's not moving? The second train. Go ahead.
Let me say, you could put V2, I at 0, so then you cancel that out.
Very good, Ed. All right, so drop that off right away. It's not even involved. We know the mass of the first train car was 1,500. We know the velocity of the first train car initially was 25 meters per second. We know the mass of the second train car is 2,500. We know that it was not moving initially. And our goal is to figure out VF. So, how do I solve for VF? How do I solve for VF? Divide by, what's the word I just said?
The quantity.
Yeah. Divide by the quantity, M1 plus M2. Very good. Divide by this. This is a coefficient. For those of you that are getting confused, because I saw this in your quiz, think of them as numbers. The masses are numbers, aren't they? So this is a number. It's a coefficient in front of VF. Like 7x. You would divide by 7 to get x by itself. So divide by that quantity, M1 plus M2. Yeah, sure, they cancel on the right-hand side, and that's exactly what we want. We want VF. On the left-hand side, please, 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 whenever you divide by the sum of something, you need parentheses on your calculator. So although I don't show them here, take a look. Put parentheses here and here. Okay, put these parentheses around M1 plus M2. Be able to remind yourself, because I keep seeing this error over and over again. Okay, you get all the physics down pat, and then it's the algebra that messes you up sometimes. So my solution is M1 V1I over the sum of M1 plus M2. That is for this specific problem. For this specific problem. If you have a problem where both objects are moving, well then you wouldn't have dropped off that M2 V2I. Right? This would not have dropped off right here. If the second train car had been moving, maybe there was a head-on collision. So they're both going toward each other like this, and they hit. Well, then they both have some sort of momentum before the
But
collision.
you couldn't cancel out the M1 and M2 if there was an M2, right?
You could not, because it's not, again, a product in the bottom. This is a sum of M1 plus M2. Remember, the only time you can cancel something of everything is if that same variable is in every single term. Look here. This has M1, but it doesn't have M2. This has M2, but it doesn't have M1. So right off the bat, there's nothing you can cancel there. Even if this was just an M1 in the bottom, sure, you could reduce these, but this M1 cannot divide into that M2 there. Okay? So when in doubt, don't cancel them out. Okay? Please, don't cancel them out if you think you're confused about it, if you're unsure. Because I'd recommend just leaving all the work in there and just plugging in the numbers into this line right here. What do you get for VF when you plug in? What do you get for the final velocity? Paul, what do you got?
9.4.
All right. That's what I got. Okay, 9.4 meters per second. Ian, if you go quickly, hurry up. So we have the velocity of the two-car or the two-train system right? Velocity of the two-train system. Now, if I want to figure out how much energy has lost, how can I go about doing that? Remember, I'm trying to think about kinetic energy here. Think about before and think about after. Marianne, give me a starting point. Not KEI, because that would assume that there is no energy loss if they're equal to each other. Yeah, we're really looking for that Q loss in this problem because we know there's energy used. So we need KEI and we need KEF to figure out what Q loss is in this problem. How do I find KEI? Kinetic energy of this problem initially. Okay.
1/2 mvi squared.
Which M? Which V?
25 meters per second and 1,500 kilograms.
Why?
Because they're the initial.
Why not the other one?
Because when you start out, the problem starts out by saying an empty train car, and it's connected, and it's moving with the initial velocity of 25 meters per second.
Okay, so that explains that part.
Yeah, and it's, well, the collision, the object that's colliding with it is M2.
And is that moving initially?
No.
Good. So technically you have a second kinetic energy, right? You've got this. You've got the kinetic energy of both objects, but the problem, or not the problem, but the thing, as Jake said, is this is 0. Okay, again, both objects have kinetic energy, or, sorry, I shouldn't say that. Both objects come into play when finding the kinetic energy before the collision. But one of the objects is not moving before the collision, so it has no kinetic energy. So it turns out that KEI in this problem does not need to be the sum of both, but just the first one. Okay? If you want to find the kinetic energy of a system beforehand, you have to find all the kinetic energies. If there were 5 objects colliding, you'd have to do this 1/2 mv1 squared, 1/2 mv2 squared, 1/2 mv3 squared, etc., etc., etc. All 5. We have 2 objects, and one of them is not moving. So this is a little bit simpler. So we're going to go ahead and calculate 1/2 m1 v1I squared to find the energy of the system before the collision. How about after the collision? How many objects are there after the collision? And answer carefully. How many objects are there? Alessia? 1. Why is there only 1 object after the collision? Why is there only 1 object? Ed? Yeah, when they link together, we've got a joint mass. What is that mass? How would I write it? I know I'm going to have my velocity squared, my final velocity. What's the mass? Yes, very good. Okay, so they link together after the 2 train cars collide with a given velocity that we determine, 9.4, of the 2-car system afterward. There's no need to even look into a second part because there is no second part. There's only 1 mass afterward, and this is it. And it's moving with a velocity of 9.4 meters per second. So you could find the energy of the system afterward just by doing that simple formula. Again, everything depends on the context of the problem. It depends on what is physically happening in the problem. This is not the same kinetic energy for every problem. It depends on what you have given in the problem. Okay, it depends on what you have given. In this problem, we were given that one object was moving ahead of time before the collision. That's this kinetic energy. The other object was not moving before the collision. Then after they collide, they move together as one object after the collision. Give me some numbers. Give me some numbers. What do you got for KEI? They're going to be rather large numbers, by the way. Give me both of them, obviously, but KEI first. What's KEI? Marcel.
468,750.
Very good. KE final. The energy in the system after the collision. Jenny. Did you use 9.3 dot 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 in your velocity, or did you use 9.4? Yeah. If you use, that's fine. 9.37 works. It's just gonna be different. I just want people to be on the same page. So if you use 9.4, you'll get 176,720, which is very close to what you had there. Yeah, in the other class, we actually used 9.37, and that's the number that they got. So that's why I recognized it right away. So you have energy beforehand, you have energy after. Why is the energy after less than the energy before? Why does the system have less energy suddenly?
I think because the object that collided took away the energy after the collision.
Yeah, the collision itself, the deformation, the crunching of that train car, the collapsing of its body, the fusion of the two cars from heat, sticking them together, causing them to be one. All of that energy went into the difference here. So if you want to find Q loss, just subtract the two. That's all you got to do. You don't even need to use that. Remember the formula, Marianne, that you said? You can use that and then just move it over, or just subtract them. You could say, well, my change in kinetic energy is final minus initial. Well, I'm going to get a negative number. That's fine. Why am I going to get a negative number? Because I've lost energy in the system. Okay, so you can find out the delta KE this way, or you could obviously find out Q loss by using that other formula that I'd mentioned. Okay? So when you subtract these two, you're going to get negative 292,030. All right? Again, significance of the negative sign is that the system lost energy. The system lost energy. So the final energy was less than the initial. So when you subtract a small number minus a bigger number, you're going to get a negative answer.
But isn't it like the absolute value Q loss? So like when it just be positive number over?
Yeah, so if the problem said determine the amount of energy, what was the exact wording? Let's see what I said. The loss in kinetic energy due to fusion and deformation of the train cars. Yeah, technically speaking, you could write that as a positive. Honestly, at the end of this problem, I wouldn't care, but as long as you explain what you're doing. Does that make sense?
Yeah.
Yeah, because if you're going to give a negative answer this way, this is fine, the way I see it. But if you started with KEI equals KEF plus Q loss, and you solve for Q loss, you get the answer, and you think, oh, that's a positive answer, that's fine. It's just the energy that's lost in the system. Okay? Either way is fine. I have no problem with either way. As long as you give some evidence, like this statement right here is my evidence. Or KEI equals KEF plus Q loss would be your evidence the other way, and you get a positive answer. So the gist of this problem is that when two objects either collide and deform or collide and stick together, you're going to lose energy in the system. And that's what this energy loss is here. Now, if they collide and separate and they don't deform and they don't stick together, you're not going to lose any energy. Let's take a look at another example of that now. Nice and loud for us. Mike, go for it.
Two objects collide elastically and head out. The first has a mass of 15 kg, 15 and initial velocity of 3.5. Velocity of the 15-pound object, or 15 kg object, is 5.875 meters per second as well. What is the final velocity of the 25 kg object? Verify the answer by calculating the total kinetic energy before and after the collision.
So I'm telling you that it's elastic in this problem, and I want you to prove that it's true, as opposed to me giving you a scenario, right? Then you find the KEs, and if the KEs are the same, you could say, oh, it's elastic. So I'm telling you it's elastic, and your goal is to prove that it's true by finding the KEs at the end of the problem. But to get the KE at the end of the problem, you need to get the velocity first, which is what you're trying to find using your conservation of momentum. So the second mass was 25. What would the second velocity be initially?
-4.
How come?
But it's moving west.
Yes. So let's demonstrate. Simple demonstration. And this is honestly what I really wanted to do with your lab with those carts that we have, but our velocity sensors are broken. I'm trying to wait on a new one to come in, so I'm trying to push the lab back. We're going to do a different lab tomorrow, you'll see. But the idea is that when two things collide, right, they're going to come together. Either they're going to stop like that, and these stop easily because there's a lot of friction, or maybe they might bounce off each other if I do it this way. They bounce off a little bit, right? So if I do a little bit faster, see how that one bounced off? So if I take this one and barely move it, and move that one a lot, we can see that one moved a lot more. So here's what's happening in this problem. We've got mass 1 moving east with 3.5 meters per second. We've got a bigger mass coming in at a higher velocity. So which of these has more momentum? This is smaller, moving slower. This is bigger and moving faster. Which has more momentum? Clearly the one that's bigger with more velocity, right? If one was bigger but had more velocity, we wouldn't really know. We'd have to find the product. But if this is bigger and has more velocity, it's got more momentum. So when these two things collide, what's going to happen for sure? This has got to be kicked off that way. Absolutely. This one, it could follow in its path, right? It could do this. It could collide, and it could move over. It could collide. This could move back a little. This could be shot off. This one we don't know about. That's what we're trying to figure out. I also know that this moves back that way because look, it says the final velocity of the 15 kilogram object is 5.875 meters per second west. So this started going east, it collided, then it went west with 5.875 meters per second velocity. The goal is to figure out what happened to this object after the collision. Okay? What happened to object 2 after the collision? So we know object 1, its velocity after the collision was negative 5.875 meters per second. By the way, the reason I'm giving you a lot of decimals here, the kinetic energy balance that we're going to see at the end works if you have exact numbers only. So I had to make this problem work, so I picked specific numbers to make it work. So don't round your answers in this one, okay? Don't round your answers, or else you'll get a small deviation. Our goal is to figure out the velocity of the second object after the collision. Okay, that's our goal right there. So what equation will I use for this one? They're colliding and then they're separating. Colliding, so it's the same beginning as the last problem, but they're separating now. They're not sticking together. So what's the equation? Jake, you want to read the whole thing?
Elastic then?
It's elastic, yep, absolutely. It is elastic. What's the equation for elastic? What do you got? So those are the momenta before the collision of each of them. Go ahead, and then afterward?
N1v1f plus N2v2f.
Yeah. And those are the momenta of the objects afterward. So just to point this out, object 1 before the collision, product of these two. Object 2 before the collision, product of these two. Object 1 after the collision, product of these two. Object 2 after the collision, product of these two. So you see what we're actually doing with this. Now, our goal is to figure out V2F. Our goal is to figure out V2F. Mathematically, think of this as a number again. Think of this as a number. So here's what I'm thinking. Don't write this. Please don't write this. That's what I'm reading in my mind right now. That's what I see. Think about it for a second. This is a number. This is a number. This is a number. This is a coefficient M2 and an unknown V2F. That's like my X, right? That's the equation that I'm seeing on the board. So for those of you that have been struggling with the math parts, I'm trying to give you more or different ways to look at this. If these are numbers, what would you do with 10 and 8? You would add them. And then how would you get rid of the 7? You'd subtract it, right? Now how would you get rid of the 4 at the very end? So why don't we subtract the 7? Or in reality, let's subtract this over this way. And then divide by this. Do you see how I'm making this analogous to just numbers now? So I'm going to subtract M1, V1F from both sides. I can't combine like terms, so please don't try to combine like terms. So again, you start by simply moving this over, those cancel, getting rid of it. So just pretty much tack it on here. For anybody that hasn't picked up on this by now, if some quantity is on the right-hand side of the equation, and you want to move that entire quantity or term to the left-hand side, just move it over and switch the sign. Right? Wasn't this positive right here a minute ago? And now it's suddenly negative. So literally, you're taking this entire term and moving it over and just switching the sign. That's the additive property of equality. You learned that, freshman year. Or maybe even before that. Now the final step, we want to get V2F. What do I divide by? Jake? M2. That is my generic solution for V2F. You're going to do this in your lab a lot tomorrow. Solve generically like this. Okay, so please practice it. Please practice it. In the beginning, I said, plug in numbers, it's fine, blah, blah. What do you got, Kira? I saw a weird look in your face. -4? -4. I don't think it can't be the same as the other one, actually, because I got around that. A few more decimals? 625. Check your work, Kira. Look at your calculator. Go through it. Retype them in. Make sure you put the right numbers in the right spots.
This is actually
Was it positive? Positive? Not negative, right? So before we get to the second part of this, where we want to verify that this is true, let's go back to our example here. So here we go. The objects came together. We knew that after they collided, this one was shot back. The question was, did this one continue this way, or did it get shot back this way? So what would your response be now, based on your answer? Think about positive. Positive means to the... Yeah. So it actually goes backwards, which is a little counterintuitive. Here's how you know. The initial velocity of object 2, wasn't it -4? If you go back. That's because, ready? Here's object 1. Here's object 2. Object 2 was going like this. Its velocity was -4. It collided with this one, which was also moving, sending that one off, and now going back at positive 1.65. Remember, motion this way was -4, so motion this way is the positive 1.65. Okay? Make sense? It's clearly a smaller number than, what was that other number? 5.875. Because this has a lot more mass. So when these collide, this had a lot less momentum. So when they collide, this one gets launched off, this one just moves off slowly. Okay, so use some intuition to help you realize that your answer is either A, correct, or B, incorrect. Now, how can I verify that energy is conserved in this problem? How can I verify this? How many objects are moving before the collision? How many objects are moving? Both, 2. How many moving after the collision? So you need to calculate 4 kinetic energies. Both kinetic energies of both objects before the collision. Add them up, you get the energy before the collision. Find the kinetic energy of both objects after the collision. Add them up, you'll get the kinetic energy of the system after the collision. Those 2 kinetic energies will be the same. So again, making that statement so you see what I'm talking about. The kinetic energy before the collision is equal to the energy of the first object before the collision and the second object before the collision. The kinetic energy after the collision is the kinetic energy of the first object after the collision plus the second object after the collision. Okay, so you just have to plug in the numbers at this point. Just so you know, they will both turn out to be, both energies, before and after, because they have to be the same, because it's conserved. The energy of the system before and after will be this number here. Okay, that's what you'll get for both of those answers for KEI and KEF. By the way, tomorrow you're going to start your lab like I was telling you. The other class is going to be working on our lab tonight. If you want to get a head start, because you're going to have some work coming up, problems, and other stuff, you can start this homework. We're not done with this section yet. We're going to still finish it, but you can start this homework if you'd like to tonight. Okay? Huh? The homework will we do? It won't be due tomorrow, but it will most likely be by the end of the week, yes. I got to look and see what dates are. Let me know if you're interested in this stuff. Next Thursday. The example says that a billiard ball traveling north, so like up the table would just mean a directional. So traveling north at a speed of 3 meters per second collides with another identical one. So you hit the cue ball, it bumps into like the 7 ball, and the 7 ball is currently at rest. The cue ball hits the 7 ball, causing the 7 ball to move forward. The ball that was moving initially stops immediately. Have you ever seen this before playing pool? When you hit the ball, you hit low on the cue ball. It's called putting like English on it. Sometimes it puts actually backspin on the ball. You hit low on the ball. You said the same thing?
Yeah,
So you're not bowling the.
and I said I put English on.
Yeah, it just means backspin.
Yeah.
So you hit low on the cue ball. When it collides with another ball, pin ball, billiard ball, I should say bowling ball on pin, the cue ball stops, and then the other ball starts moving. All right? So that's what we know about this problem. The question is, with what speed does the other ball start moving with after the collision? And after the collision, what physically is happening?
So it would be, would it be an elastic collision?
I don't know, which one? You're saying with not much confidence. What's happening? Describe what's happening, Jake.
One object moving in the,
Listen, please.
I think it would be an inelastic collision because they're not moving in each other. One is hitting the other. They're not both moving in each other.
Okay, but that doesn't classify whether they're moving or not before. It's afterward whether they stick together or not. That's how we differentiate it.
So it'd be
Keeps happening.
it'd be an elastic because they don't stick together.
Yeah. So it's elastic because they don't stick together. Remember, the easy way to remember inelastic is when they do stick together. Thanks. When they do stick together, it's inelastic. And remember what I mentioned yesterday, please. No real example is going to be perfectly elastic or perfectly inelastic. Usually it's in between. So in real life, it's a combination of these. Now, for this case, you have a pool ball moving, hits the other one, and then the other one's moving. They do not stick together. If they don't stick together, then we say it's elastic. It's probably not perfectly elastic because there's going to be some energy loss, but we'll assume it's elastic for now. And then we'll see what the energy loss is if there isn't.
Doesn't it just say elastic collision right there though? Does that not matter?
Did I say that? Oh, I did say that. All right, well, I said it in the word problem. I didn't realize that. I'm going to get rid of this next year. Just say in the collision. Thank you, Victoria. It's a good point. Okay, if it says it, then obviously use what it says. So let's draw a quick diagram. Here's the cue ball. It's moving forward. Here's the 7 ball right here. This is before the collision. Then after the collision, the cue ball hits the 7 ball and it stops. And now the 7 ball itself starts to move forward. Okay, so that's physically what's happening. Now, if I were to look at my general equation for elastic collisions where they don't stick together, what would that be? What's my equation where they do not stick together to each other?
M1 V1 I plus M2 V2 I equals M1 V1 F plus M2 V2 F.
Yeah. All right, so think about this. Remember from last time, we talked about this already. This is the sum of the momenta before the collision. So initial, initial. This is a plus sign here. Some people have been putting minus signs. Make sure you make that correction. At the end of the problem, on the right-hand side of the equation, this is the velocity after the collision and after the collision. Which of these two can we immediately ignore or set to 0? Which of these two can we ignore? There's 2 terms. There's 4 terms total. 2 of them do not actually affect the problem. What are those? Okay, that's one of them because assuming we call this object 2 and object 1, right? And then? It's moving afterward. Yeah. Remember, this is object 1. And this is at rest after the collision. So that's at rest after the collision like that. So the first object is the cue ball. It's moving. The second object is at rest. So we can drop off M2 V2I. Then collision occurs. It hits. The first ball, the cue ball, now stops. So now it's at rest, so that drops off. But this ball gets propelled forward. Okay?
Does it matter if we write does it matter where we put the first and second object in this formula?
It doesn't matter as long as you're consistent.
Because I put M1 plus M2. Oh, wait.
That does matter, yes.
Can I do like M1 plus M? No, I mean.
You can only do, listen, Jake, only time you ever sum the masses together,
I screwed that.
that's okay, but just for everybody, not just, Anytime you sum the masses together, it's when it's inelastic or when they stick together. Okay, or remember the example, who came up for this example? It was really lame, but it was like two skaters, and I had you guys push off each other from the chair.
Victoria and Michael.
You were Michael? Oh yes, that's right. Okay. This is kind of funny. That's also inelastic because you start together and then you push apart from one another. Okay, so any problem where either you end together or start together, the two masses, is inelastic, and those are the scenarios where M1 and M2 would be summed together. Imagine, well, I'm not going to go into it, okay? Let's continue with this problem for now. I was going to do a conceptual thing, yeah.
So do we know what Z1I is?
Well, that's where we have to go back. Let's look at the problem. The billiard ball initially is traveling with a given speed of 3 meters per second. That's the first billiard ball that hits the other one. So V1I is 3 meters per second. But that's all we know. What are we trying to figure out? Mike? Good. Of which object? Yeah. Okay, so this is what we know and what we're looking for. That's it in the top right corner. We're not given anything about the masses. We're not given anything about the masses. Paul? Because they're the same. It says the two billiard balls are identical. They're identical, which means that you can, instead of calling them M1 and M2, just call them both what? M. So let's go ahead down here. First of all, let's write what's left over from these two. M1 V1I equals M2 V2F. That's what's left after we, ignore these terms right here. Then we could say to ourselves, well, M1 and M2 are the same thing, really. So if you have the same thing on both sides of the equation, Jake, they cancel. So again, either just erase the subscripts, like this. Okay, erase the subscripts, and then you'll realize, well, M is on both sides because they're the same, so M cancels because it's on both sides of the equation. You could have also have done this up here. You could have erased all the subscripts up here and canceled all the M's to start instead and said M's all cancel. Just take it off. Don't worry about it, guys. This is falling off like 6 times today off the wall. Every time we put it back up with more tape, it just keeps coming off. So what this leaves us with is V1I equals V2F. V1I equals V2F. What's the significance of that statement?
Is it 3 meters per second?
Yeah, why is that? What's happening here?
Same.
It's the same. So you have this object moving, it hits this object, but then it stops. So all of that momentum has to go somewhere. Where does it go? Into the other billiard ball. So therefore, they got to have the same velocities. And this is assuming there's no energy loss because it's elastic. Remember, the best example of elastic collisions we can really do are like metal on ice or hockey pucks on ice when they collide. Those are pretty good examples too. Billiard balls are pretty close as well. In real life, obviously, there's going to be some sort of energy loss when they collide. Okay, but we're assuming it's elastic, so we don't have to worry about that.
So in every elastic collision, there's no Q loss?
Correct. That was what we said yesterday. Very good. We said that KEI equals KEF in all elastic collisions because there's no Q loss. Okay? Now, what you would make as a statement here, first of all, yes, you're right, the answer is 3. Because V1I was 3, so we put a 3 there. And therefore, that's what V2F is equal to. This problem shows you what's called the complete transfer of momentum, which doesn't happen often. Okay, this is a complete transfer of momentum. Usually when two objects collide, they both move afterward, or some of them move in some fashion or another. But if an object stops after colliding with the other object, it's a complete transfer of momentum. Now, another thing that you should write down. Whenever you have an elastic collision, again, whenever you have an elastic collision, if the masses are identical, they're going to drop off. They're going to cancel out. It always works that way. Again, whenever you have an elastic collision and the masses are the same, all the masses are going to cancel, which leaves you with only velocities left behind. That's why we ended up with only velocities here. No masses are involved. Okay, that's like the mass canceling when we looked at energy. when we set potential and kinetic energy equal to one another, and we solved for V, and we got radical 2gy in the last chapter. The mass has dropped off because they're on both sides of the equation. Well, here as well, you have mass in all terms in the equation.
Is this like the same thing as Newton's trivial?
Yeah, absolutely. Newton's
The
cradle
transfer, like
is
the
Newton's
transfer.
cradle is both conservation of energy and momentum. Yes, and it's circular momentum, not linear momentum. So it's a little different, but it's the same idea, the same concept. Yeah, because one object hits and it stops, and then it stops, and then it stops. So you're transferring that momentum, but there are small amounts of energy loss on every collision, no matter what.
Just
Always,
stops eventually.
because eventually it'll stop. Okay, it's a good analogy we did there, Jake. Very good. Okay, Josh, I saw your hand. Did I answer your question? You sure? Okay. All right. Let's go. Example 4. I really like this example because when I taught forensic science last year, I taught some of the students, all of them, hopefully they all learned it. I taught them about what's called a ballistic pendulum, and I mentioned this earlier in the year, and this was an older way to measure the velocity of an object. Now, specifically a bullet. So imagine you didn't have a speedometer, right, a radar gun, and you couldn't measure the speed of something moving. If you are able to fire a bullet or an object, it doesn't matter what the object is, and embed it into another object. So imagine on this end, you've got like a rope, and you've got a mass, like a block hanging from that rope, and the bullet hits the object, sticks into it, and it causes it to swing up like a pendulum. If you're able to know the height only that it moved up to, you can measure the initial velocity using conservation of energy. Now, this also uses conservation of momentum, and this example is similar to that. Okay, but before we start doing that one with the ballistic pendulum, we're going to need to do a little bit of circular motion. So we'll take a look at one where it's not going to be moving on an arced path. But in this example now, we've got an object sitting, a cart, and you fire something at the cart. The cart is made of clay. It hits the cart, sticks into it, and then they move together afterward. So what kind of a collision is this going to be in this problem then?
Inelastic,
Why?
because they're sticking together.
Yeah, inelastic because they fuse or stick together. Alright, so we know that already. Now, the pellet, the bullet, pellet, right, pellet gun, has a mass of m. Okay, it's not given, a mass of m. And it's fired with a given velocity of 24 meters per second into a resting clay cart. The cart might be on wheels, alright? The cart has a mass 11 times that of the pellet. 11 times more than the pellet. From the information, determine the velocity of the combination after the collision, and then the amount of energy loss in terms of m. In terms of m. So, let's look at part A first. What can I list as my givens here? What can I list as some givens, Jenny?
Initial velocity 1 is 24 meters per second. Initial velocity 2 is 0 meters per second. Mass is m. Mass 2 is 11 m.
Yeah, very good. Okay, everything given from the problem. Now, please make a note if you need to, because some of you review your notes, but sometimes make mistakes when reviewing. For example, last year I remember a student that was studying the notes told me, well, this is 11 meters. I'm like, oh no, it's not meters. You just look back at your notes and you saw m and put meters. This m is one mass unit, okay, or one pellet mass. So the mass 1, or the mass of the pellet is m. The mass of the cart is 11m, right? Because it's 11 times the mass of the pellet. The velocity of the pellet is 24 meters per second. The cart is at rest, so it's 0. Now, remember, the pellet is going to embed itself into the cart. So we have the velocity of the pellet-cart combo that we're looking for afterward. So we're looking for VF in general. Not V1F, not V2F, just VF because they're one entity. So what's my equation going to look like for this one? What's my equation going to look like? Before the collision, what object is moving? The pellet. And that's object 1, right? So M1, V1I is definitely there. Is the cart moving before the collision? So technically I could just put plus 0 or just leave that blank. Whichever you'd like. I mean, we've been putting M2, V2I, and then we cross it out. but by this point in time, if you notice that something isn't moving, either before or after the collision, just put a 0 in that spot or leave it blank completely. Okay? So again, these are your little crib notes here, okay? This is the pellet, and this is the cart. And that's before the collision. After the collision, what do you know? After the collision. Victoria?
Those masses combined,
Good.
they're entity.
Very good.
The quantity is M1 plus M2
Very good. I like that. The quantity times.
times VF.
Good. Again, after the collision occurs, the pellet is stuck in the clay cart. They move together as one entity or one object. Good. So M1 plus M2 is the mass. They have one velocity, that combined velocity, whatever it is, together. They're both moving at the same rate. So it's only a VF there. So, not that tough of a problem, except now we know mass. But I do know something. What should I do at this point in time? I do know something else that I can do. Yeah, Jake.
Get VF by itself.
Okay, let's get VF by itself. We can do that. You want to solve for VF? Let's do that. So this is not here. How do I get rid of the quantity M1 plus M2? Divide by it.
Well, why are we getting rid of the 0 then? Because it's just 0.
Because, well, anything plus 0 is itself. Remember the 0 identity property from math? It means that anything plus 0 is identical to itself. So that's what VF turns out to be. It's this momentum of the pellet divided by the sum of the masses. But it still looks like we have a problem because all we have is this. Right? All we're given is this velocity. What about these? What can I do with these? So your hand pop up.
I was gonna say cancel, but you can't.
You're good in a minute, but you need to do something first. Alright, so either we put numbers in their places, that's fine, or 1m and 11m, okay? So recall, please, look up here. M1 was given as m. M2 was 11m. So let's replace those. So this is really just m. This is m plus 11m. And then we still have v1i. Yes?
Why can't you cancel the M1?
The denominator is a binomial. And you can only cancel something if it's a monomial. So if you had just m in the bottom, like this, then sure, you can cancel the m1s. These are add-ends, right? They're adding together. The only time you cancel things vertically is if they're factors. So if this had been m1 times m2, you could cancel the m1s. Okay? Guys, focus. Focus. Come on. Too much chatter there. Now, m1 is the mass of the pellet. So it goes here and up there, right? These two spots. And the mass of the cart is 11 times that. So now, as a result, it looks like we still can't cancel, but we can combine these like terms. What's m plus 11m? 12m. So now we're going to see that we can cancel them. Okay? So we've got the m's in both spots. So now, Alessia, this is what I was alluding to. The m's are now factors because they're all multipliers. So this m cancels with this m right here. So as a result, the velocity at the end of the combination is the same as the initial velocity of one of them, but divided by 12. Where does the 12 really come from? Where does the number 12 come from in this problem? What significance does it have? Oops. Yeah, it's the combined masses. You added them and got that. A lot of the time you're going to see this when you're looking for VF for an inelastic equation. You're going to be dividing by the sum of the masses like we did in the very beginning. So this denominator is most likely going to be the sum of the masses when you're solving for VF. Okay? The initial velocity was 24 for the pellet. So now it's just 24 over 12, which is 2. All right, this was really 24 right here. It was given in the problem, the mass of the velocity of the pellet. So that's the velocity of the pellet cart combination after the pellet has been embedded into the cart. Okay? So this is significantly less. Why is it less? Why is it less? Because there's okay, there's energy loss. I mean, elsewise there's other reasons too. Definitely there's energy loss. There's more mass now. So imagine, like, remember we alluded to that example I talked. Did I mention this, guys? The football player with the sled. Imagine a football player. You ever see football players warm up or practice? They have to run into a sled and like drive this sled a few feet.
Yeah.
Well, they're running pretty fast. When they hit the sled, they must slow down, right? Because now they're pushing a lot more mass. That's this. The pellet is only moving its own mass. Then suddenly it hits the cart. Now it's got to propel the cart and the pellet forward together. So since there's more mass, there's more inertia, and inertia is the desire to stay at rest. So the cart wants to stay at rest, the pellet doesn't want to, they have a little battle there. The pellet overpowers the cart and they start moving, but they don't move with the same velocity that they were moving with initially. Okay? How about part B of this problem? What does part B say? Can somebody read that for us? Josh, go ahead.
In terms of M, the amount of energy needed for the pellet to embed itself.
The energy needed for the pellet to embed itself. And in terms of M, what the heck does that mean? What does it mean when you hear in terms of M? You should have heard of this in math at some point in your mathematical careers. When you hear in terms of. In terms of. Nobody remembers that?
Doesn't it just mean that you don't write an actual number, you just write it like as n something?
Yes, that's exactly right, Alessia. Very good. It's when you don't know the value of something, you leave it in terms of it, so it's going to be in the answer. So your answer might be like 35m or 75m. So when you read, you should write this down, because this is good for your SAT for math also. When you read that something says in terms of blank, that blank has to be in the answer. So if I said solve for x in terms of y, it would be like x equals 3y plus 8. Okay, so in terms of some number or some blank means it's going to be in the answer. So in terms of m means that m will be in our answer for the energy needed for the pellet to embed itself. Now, think back to yesterday with inelastic collisions. I have a certain amount of kinetic energy before the collision. I have a certain amount of kinetic energy after the collision. If they're the same energy, then it's elastic. If they're not the same, then it's inelastic, as we're seeing. So it's that difference in energy that we're really looking for here. If the amount of energy that the bullet has originally is, 7 joules. I'm going to pick an easy number. And then afterward, the bullet and cart combination have 5 joules of energy. Where do those 2 joules go? Because energy can't be created nor destroyed. It had 7 joules of energy by itself, the pellet. It hits the cart, they slow down a lot, now it's only got, say, 5 joules of energy. Where's the 2 missing energy joule, or 2 missing joules of energy?
Or is that Q loss or was it Q?
Yeah, that's Q loss, or the energy lost due to what in this situation? Friction or fusion. It is friction, it's a form of friction, right? But it's the fusion of them together. The energy actually takes the pellet to penetrate the surface of the cart and embed itself into the cart. Okay? That's the energy that we're looking for in this problem. So instead of trying to figure out how do you find that energy, just look for the kinetic energy beforehand, look for the kinetic energy afterward, look at the difference in those two values, and that will be the missing energy. That's where the energy went. So how do I find kinetic energy beforehand? How do I find KEI, the energy beforehand? Jake?
1/2 mvi squared.
Okay.
M1 v1 squared plus 1/2 m2 v2 squared.
Now, is the cart moving initially?
Oh, no.
So do I need that?
No.
But you're right, that's what it would be. Again, that's the kinetic energy of the bullet, or the pellet rather. The cart would have another, it would be plus 1/2 m2 v2y squared for the cart. But because you know the cart isn't moving before the collision, there's no need to find the energy of the cart because it's 0 before the collision. It's sitting still. There's no energy. Now, that's beforehand. I know the mass is m. I know the velocity is 24, so I plug those in. Bless you. So instead of M1, I just put M now. And VI was 24. What's 24 squared going to give me? And then half of that? Yes, something with a 6. Very good. Because 4 times 4, right? Good. Unless you're using number sense.
Never mind.
Half of it comes out to be 288. Good. It's 576, but half of 576 is 288. M. And my units of energy are? Yeah, believe it or not. Okay? 288 M joules. Now, if I told you the mass of the pellet is 5 grams, you plug in 0.005 and you get your answer. A pellet's not going to be measured in kilograms, right? Think about it. Wouldn't, like a kilogram is 2.2 pounds. A bullet would never be 2.5 or 2.5 pounds. It doesn't make sense logically. So it'd probably be given in grams. So if you're given the mass, you can plug it in and actually find the actual energy. Okay, this is in terms of M. Before the collision. What about after the collision now? After the collision now. What do we have? Somebody else. Give me a sec, Jake. You did it beforehand. Let's do after now. Somebody that hasn't answered yet today. Let's mix it up. I'm seeing the same hands. You didn't answer yet? Maybe? Maybe not? Let's hear it.
We're just moving that
After the collision, how many objects are moving? But it is the sum of both the masses. Isn't the pellet in the cart? Give me like another 30 seconds. The pellet is embedded in the cart, and they move together after the collision. They're moving together physically.
Is the quantity of M1 plus M2?
Yeah. The quantity M1 plus M2 times, go ahead, keep going.
VF.
Good. Okay, now the masses, as we know, are M and 11M. The velocity was 2. Therefore, my final kinetic energy is going to be really, looks like 12M, right? 12M times 4, which is 48M, times 1/2, which is 24M. So before the collision, look at the amount of energy. 288 M joules. After, only 24 M joules. Logically, it makes sense. The energy has to go down because you expended that energy to embed itself in the cart. So just subtract the 2. Okay, you're going to get 264 M. That's the amount of energy needed. Again, take final, right here, minus initial. You get negative 264 M joules, meaning the scenario lost that much energy in order to stick into the cart and cause it to move.